Welcome to our flexible AC transmission system video lecture series. Today we are going to discuss, we have already discussed actually the comparison between SBC and the STATCOM. We shall see detail today what are the control features of the STATCOM, that is the title of this topic will be the external control design of the static Var compensator or SBC. Now, as we know that primary objective of applying the static compensator in a power system is to increase the power transmission capability. This is a basic principle of putting a fax devices. Since static compensator cannot generate or absorb real power, we have to neglect the switching losses of the SVC, and we should now presently eliminate the idea of putting active component or the storage component within a STATCOM, neglecting the relatively low internal losses of the SBC and assuming that no energy storage for the STATCOM. The power transmission line system is affected indirectly by the voltage control, that is the reactive power, the capacitive or inductive of the compensator is varied to control the voltage at the given terminal of the transmission network. So, the basic compensation needs usually into the following two categories. One, the voltage support, direct voltage support to maintain sufficient line voltage, facilitating increase in the power flow under heavy load and for preventing voltage instability. This is maybe the purpose. Another is the transient stability. The transient and the dynamic stability improvement to increase the fast swing stability merging and provide damping to the power oscillation. So, in order to meet these two demand, general compensation requirement of the power system, the output of the static Var generator is required to be controlled to maintain or vary the voltage at the point of the connections of the transmission line. So, this is the one of the desired feature of SVC. In general, the control scheme converting static Var compensator either to a control impedance or a converter type into a transmission line compensator. The power system at the terminal of the compensator is represented by the generator with a generally varying rotor angle with the internal voltage P. So, we know that actually P is given by V1 V2 by x sin delta. So, where delta is the rotor angle and the source impedance Z is a function of the angular frequency at a time t. The terminal voltage, that is Vt of the power system can be characterized by the generally varying the amplitude Vt with an angular frequency P. This is the way we model it. So, this is the general control scheme of SVC. What happen? You have a prime mover that generates the voltage. So, with an angle V and with voltage V, amplitude V and that angle delta. So, this is the network, and here you put a static Var generator. Essentially, it does not have any power to compensate the real power. So, P is 0, this is a converter based, and it may be actually TCSC or TCR. So, how you will control it? So, essentially you will measure the voltage. So, you will check that whether there is a sag into the system or not. So, accordingly we will actually check the system capability. So, there is an auxiliary input, there is a V reference, from there we will check that whether there is a sag in input or not. And also if it is not so, then you will put this value of the Vt as a V reference, and thus actually del V becomes 0. and you also have a auxiliary inputs. And from there, actually you have a direct input, and from there you essentially you compute what is your IQ reference. This IQ reference you may get a hybrid StatCom, or you may have this kind of control devices, so that you require to inject the voltage proportional to the IQ ref. The output of the static Var generator is controlled so that the amplitude I0 of the reactive current is drawn from the power system and the reference current IQ ref. With the basic compensator control, the Var generator is operated at a perfect terminal voltage regulator. So, that is something we have maintained. The amplitude Vt of the terminal voltage is measured and compared with the reference voltage Vref and produce an error. This error is fed to the PI controller. This Vt is processed and multiplied by a PI controller to provide the current reference IQ ref for the compensation of the Var. This is the principal operation of this SBC. If the proper compensation of the reactive power system requires some specific variation of the amplitude of the terminal voltage, and that is varied from the auxiliary input. Sometimes it may sag may occur or something, so or maybe a disturbance due to that, then we actually work on the auxiliary input. The following sections, some practical auxiliary control loops are corresponding to these following items will be discussed. That is the slope regulation, dynamic performance, transient stability, and the power damping. So, these are the 4 entities mostly. We will be actually we will see that what are the control technique will require to achieve those entities. Now, many applications the static compensator is not used as a perfect terminal voltage regulator, but rather terminal voltage is allowed to vary proportional to the compensating current most of the cases. Why it is proportional to the compensating current? We know that actually reactive power handling capability varies with the QSK in case of the SBC. The linear operating range of the compensator with a given maximum capacitor and inductive current can be extended if the regulation drop is allowed. So, then it will be linear, otherwise it is quadratic. Regulation drop means the terminal voltage allowed to be smaller than the nominal no load value at full capacitive compensation, and conversely it is allowed to be the higher than the nominal value at full inductive compensation. This is the drop regulation. So, that is what happened. The perfect regulation, that means the zero droop or slope, could result in purely defined operating point and has a tendency to oscillate. So, that is something we require to prevent. The regulation droop or the slope tend to ensure automatic load sharing between static Var compensator as well as the voltage regulating device normally employed to control the transmission voltage. The desired terminal voltage versus the output current characteristics of the compensator can be established by a minor control loop using actually as we have shown a previously defined auxiliary input. So, that will be used for the droop control. Droop control is very important feature while the multiple entities working on how they will share the load. Ultimately, let us assume that power system all of a sudden you have del V comes into the picture. So, you have a swell in voltage, and thus what happened, this Vt will be added up and this current will be sensed current sensing and the processing circuit, and the measuring voltage also measured and will add up Vt plus del Vt. So, the error del Vt will come and will give you the reference, and perfect regulator when Vt equal to Vref and del Vt equal to 0 and Vref equal to, generally it is Vref minus k into, where k is the gain of this proportional controller, into IQ. Thus, it will ensure the sharing of this reactive power between all the element. Implementation of the Vi slope by minor control loop, changing the reference voltage in proportion to the line current. So, how the line current changes, you actually inject some extra voltage, and that is called the droop control feature. So, how you will calculate k, that is also a challenge. We have written that I into k into I. The proportional, a signal proportional to the amplitude of the compensating current k IQ with an order of the polarity, capacitive current is negative and the inductive current is positive, is derived. Sum to the reference Vref, then obtained the effective V reference, then the V reference will change dynamically as it will be required by the I. So, where k is the regulating slope, where k is given by del Vc max by C max or del Vcl max by IL max, depending on the whether you have a capacitive or the inductive compensation, where the del Vc max is the deviation or decrease in the terminal voltage from its nominal value and the maximum capacitive current. But by using this reference, the amplitude of the terminal voltage Vt is regulated at a linear slope over the control range of the compensator. For terminal voltage range outside the linear control range, the output current of the compensator is defined by the basic Vi characteristics of the Var generator. Let us see this curve and that will explain the case. Let us consider that the load line 1 intersects a Vi curve. So, this is the load line 1 and this is the load line 1 and the characteristics of the nominal reference voltage, and thus what happened, the output current of the compensator is 0, and this is actually the load line 2. Load line 2 is below the load line 1 due to decrease in the power system voltage, that means the generator outage or something like that, or SAC. It interaction with the compensator and calls for the capacitive compensation of current IC2. So, there will be some current, it will be difference. Same way, if there is voltage swell up and the load line 3 is above the load line 1 due to the increase in the power system voltage, maybe due to the load rejections, the intersection with the compensator and calls for the inducting compensation of current L3. So, there will be some amount of extra current will come. So, if it is a STATCOM, then it will have this kind of characteristics, and if it is SVC, you have a linear characteristics, and this is the actually without compensation. Now, the terminal voltage variation with the compensation in the linear operating range under steady state condition and slow system change is entirely determined by the regulation loop, that is called droop control, independent of the type of the Var generator used, both it can be SVC or STATCOM. Outside the linear operating range, STATCOM and SVC act differently. So, that is the challenge. The dynamic performance of the two types of compensator also will be different, please note that. So, let us see the dynamic performance. The dynamic behavior of the compensator in the normal compensating range can be characterized by using a basic transfer function, and therefore, the terminal voltage V t is V 1 plus G 1 G 2 H x plus V ref G 1 G 2 x 1 plus G 1 G 2 H x. I am coming to it. So, where G 1 is a regulator, G 2 is a Var generator, and X is a system impedance, and H is actually the transfer function of the measuring devices. The object is to establish how well terminal voltage is regulated against the varying system voltage. So, that is something we require to put it. Let us assume that V ref equal to 0 and consider the small variation only. So, then amplitude of the variation of the terminal voltage V t against the amplitude variation of the power system del V can be expressed in this term. At the steady state, this becomes just 1 by 1 plus x by k. This confirms that the slope becomes smaller if k becomes large. The terminal voltage remains constant independent of the system variation. Similar with the increasing k slope, the terminal voltage becomes unregulated. So, we require to keep this dynamic performance into the mind. The equation shows that the dynamic behavior of the compensator is a function of the power system impedance. So, SBC basically changes the power system impedance. Therefore, time response and thus the stability of the control is dependent on the system impedance. So, this is something we require to keep in mind. Now, transient stability with SBC. This transient stability indicates the capability of the power system to recover from the major disturbance. Transient stability at a given power level or the fault clearing time is primarily determined by the power it is actually handling at that moment and the torque angle delta and the post fault system condition. The static compensator controlled to regulate the terminal voltage, we have seen that, can increase the transient stability by maintaining the transmission line voltage in the face of the increased power flow countered immediately after the fault clearing. So, this is something that SBC can do and thus increases the transient stability. This transient stability can be increased further by temporarily increasing the voltage above the regulation reference for the duration of the first accelerating period of the machine. What it will do then? What will happen then? The voltage increase above its nominal voltage value will increase the electric power transmitted, because you have V1, V2, if V2 is increasing, so power handling capability increases and thus increases also the deceleration of the machine. The plot marked Vm equal to V, I shall come now, represents the P versus delta power obtained with the ideal compensator holding midpoint voltage constant. So, see that this is the case. So, this is the area and this is the case with the STATCOM and this is the case with the SBC. So, this is the SBC and this is basically the STATCOM. So, the plot marks STATCOM and SBC, this compensator with the given rating is sufficient to maintain the constant midpoint voltage for the total angle delta, because this is basically 0 to pi. So, thus it increases the transient stability. The implementation of the transient stability enhances the basic control scheme and can be accomplished by simply by summing a signal del V to the fixed voltage reference V ref. This signal del V can be derived from the rate of change of the transmitted power. If you see that there is a change of transmitted power, it can be changed. The line current or the system frequency indicating that the angular change of the disturbed machine. From there we can calculate what should be the del V change, and thus we can incorporate it. Let us see that how does it work. So, power system with fault, so del V has been increased. So, this is basically the change of frequency and the change of voltage. So, ultimately it will be actually sinking the current I0, and we have for this since it is a del V has been increased. So, we will increase the actually the terminal voltage by del V. So, ultimately you got a Vref, and Vref will be added with the del V, and thus this Q will come, and the system parameter indicates that if fault has recovered. So, from this parameter we can see that fault has recovered. So, in a post fault session it can act and compensate first. So, implementing the transient stability enhancement concept by increasing the reference voltage during the first swing of the major disturbance will try to help us to stabilize the system shown, and hence SVC can or restore the system faster. Another main features of this actually SVC is definitely the power oscillation damping. Power oscillation damping we have discussed several times. Damping is generally requires the variation of the voltage at the terminal of the compensator in proportional to the rate of change of the effective rotor power angle. The rotor angle changes, and thus what happens results frequency and the real power variation. In practice, usually the variation of the transmitted real power or the system frequency is measured and used for controlling the Var output to produce the terminal voltage variation desired. So, how you will do that? Function of the control scheme definitely is to damping the power oscillation. In this general idea of modifying the fixed voltage difference by auxiliary control signal to derive the effective voltage difference, the voltage difference will change them. Accordingly, a signal correspond to the variation of the real power or that of the system frequency is sum up with the fixed reference Vref. The added signal causes the output current and the compensator to vary or change, and on the fixed point to control the terminal voltage, and thus it will damp out the oscillation. So, this is the case. Again you have this thing. So, del V, and in this case what will happen, actually you will add up. So, basically P dt you will increase, so that ultimately you will add up this, so that power flow frequency variation circuit it can measure, and accordingly so you will actually you will fit the V reference. So, this will give you a delta change, and this delta will be then varying according to the power oscillation, and that value will give you a varying IQ reference, and that will essentially damp out the oscillation. So, Var Reserve, even in the area of the voltage regulation, the static compensator is viewed as primarily as a fast source to counteract the rapid or unexpected voltage disturbance due to fault, line load switching, etc. To fulfill this application requirement, it is necessary to ensure that the compensator will have sufficient Var capability to handle the unpredictable dynamic disturbances. The basic concept is to allow the compensator to change its output rapidly to encounter this transient disturbance. So, we require to have a huge inbuilt Var handling capability. A possible scheme to implement the basic Var control, the magnitude of the output current of the compensator is measured and compared against the reference IQ. The error signal VQ is then processed by the integrator of the large time constant and added to the fixed value of the voltage difference. What happens then? This forces the input signal of the voltage to regulate the change until the difference between the actual output current and the compensator and the steady state output current reference become equal. So, this is a way to achieve it. So, this is the Var Reserve capability, and so what happens is a slow integrator. So, it measures the current, you have IQ reference, so it will integrate, and ultimately this will change the terminal voltage, and in that way it will control the reference. Thank you for your attention. This is the control technique of the SBC. We shall continue with the next class with some control technique of the SBC. Thereafter, we shall discuss about some entities and application of the STATCOM. Then we shall switch over to the series compensation. Thank you so much for your attention.